network planning and design. In this nugget, we'll be talking about network design, and we'll take a look at kind of common networking scenarios, which of course will include a DMZ or perimeter network, as Microsoft calls them. And so, even though Microsoft in certain parts of their organization is kind of starting to say goodbye to DMZs, the official Microsoft answer is still to use DMZs, and we'll look at that. And then we'll take a look at horizontal and vertical networks. Horizontal networks representing various floors within an organization, and vertical networks usually representing a backbone. You'll see about connecting multiple hosts together on a single floor, for example, in a multi-floor environment, with hubs. You could use hubs, but they're a little bit chatty. Probably a better solution in many cases will be to use switches, which we'll talk about shortly here. Then your routers can break up both your collision domain and your broadcast domain, help to make your network traffic more efficient. And they're also useful in breaking up the logical subnetting of your networks. And we'll look more about subnetting in an upcoming nugget here shortly. You'll also take a look at switches here. Switches are often replacing hubs and sometimes even routers because they're very fast, very efficient, and they're not as chatty as a hub. And we'll finalize this all by looking at some of the physical security requirements, again, that you might want to implement. You know, it's a lot of fun to design a network and just sit down with Visio and put down exactly where you want the routers to go, what you want the physical network to look like, the logical network, your IP subnetting scheme. All that kind of stuff can be really cool. You sit down with the building blueprints, design around all the walls. However, very seldom, if ever, do we get to match our actual physical network to what we draw out on Visio. Now, some of you also are just inheriting networks. In fact, probably most of us are going to be inheriting networks that somebody else has designed. Many of them have been designed very well, and you may have no reason to find fault with the way they were designed at all. Others of us have found networks that were designed very poorly. I had an associate in the Midwest that was an IT guy that kind of inherited an IT department at a community college there. And the guy that was there before him was just a college professor who they had decided would be the network administrator because he was in the sciences department, so he must be really smart, right? Well, this rocket scientist guy, or whoever he was, had decided that there would be no slack in any patch cable anywhere. So any of the cables that went into the hub or the switch, he would string them so tautly that at times they would pop right out of the RJ45 socket. I mean, it was just that tight. Well, that's just poor network design on so many different levels I can't even begin to say. Another example, when I moved into Phoenix here, I moved here because I was offered a job back in 1996 to become kind of an NT4 evangelist. I should have just worked for Microsoft, I guess. An NT4 evangelist for a company. And this company would send speakers out to convention centers throughout the United States, and I also went to England, and we would preach NT4, and there would be, about 1,000 people in some of these audiences in these convention centers. Well, as it turns out, we were only a company of about 12 people, because we just had a bunch of speakers and one IT guy that stayed at home, not me, some other guy, and he managed the network. Well, turns out that we had one little server in a storage closet. It was not even a server room, did not have environmental controls, no halon dump going on if things caught on fire, no even an air conditioning duct. There was not even an air conditioning duct in this room. And the only redundancy was a nightly backup. Well, we also had an external RAID array on that network. In any case, this was when we were riding the .com wave and everything was growing real fast and all that kind of thing, back in the days of wine and roses. And we had a growth where we had grown to about 500 people in this company. Well, it didn't occur to the network administrator there that we ought to upgrade the server. And by the way, it's kind of embarrassing to admit now, but even though we were the NT4 administrators and the NT4 evangelists, the server we ran was Novell NetWare 3.11. Don't tell anybody. Well, it ran into a number of different problems. First of all, there was a big picture window in that server room that looked out into a brick wall, so nobody could really see it that there was a server room there. But the sun would beat down in there, and it was not air conditioned. So one day, the RAID array actually caught on fire, so that was no fun. And then another thing that happened was it was just a wooden door with a lock on it. And one night, a friend of mine was working late. He heard some kind of strange noises. Goes around the corner. There were these guys who had smashed the wooden door and started to cart off network equipment and some new laptops we had just gotten in that were still in the boxes. So it was pretty much the poster child network for what not to do. I mean, there was no environmental controls. There was really no security. There was no real redundancy besides a nightly backup. And the network administrator did not account for the growth that took place. Now, like I said, you can't always get the ideal diagram, the ideal network. However, you need to start with that at least, and then you need to work around whatever compromises you need to make, whether it's a supervisor or a manager that for whatever good or bad reason, just says you can't do it the way you want to do it, or you have a literal wall that you can't get through. Maybe there's a brick wall that's been built as a matter of construction in an old building that doesn't show up on the blueprints. Well, now you got to work around that. So there's different things that you have to work around at times. But let's take a look at this scenario where we'll start off with something of an idealized environment, and then you can make corrections or implementations that change this however necessary. Now, this is also going to be possibly different than many of your situations because you don't have 3 floors like I've got here, or you have other limitations. But from a conceptual standpoint, we'll try to make some things in common here that might apply to a lot of different networks. First of all, for example, here we've got the internet. Just about everybody's got to have the internet nowadays, right? So there's the internet, which connects to a router out here, and then there's another router here, and in between we have our perimeter network, or many of us just call this colloquially a DMZ, and Microsoft calls it a perimeter network these days. And despite the fact that earlier I had mentioned that many Microsoft managers are trying to even move away from the DMZ, thinking that it's a waste of time, the official answer from Microsoft is still that we need to have DMZs. And so we will kind of still consider that we will always have a DMZ until I tell you otherwise, I guess. Anyway, within your DMZ, you'll have a number of different kinds of servers depending on what your purposes are. Do you have a public internet presence? Well, if it's a pretty big public internet presence and you want to manage it all yourself, you might have your own web servers here. A lot of times you'll also have a colo out here, a co-location service. We just call them colos. And you'll have your web servers out here, and then you just connect to them through the internet yourself, and then you have a remote username and password that administrators can manage those web servers on. So there might be something like that out here, or any other kind of server that you want someone else to manage. Another advantage of this is it's kind of cheap, can be kind of cheaper, because if you don't have room or the facilities of your own to host a whole web farm, well, you can use a colo out here, and usually the prices are fairly reasonable for what you get. You get great environmental controls, high-power UPSs that have virtually 100% uptime guaranteed. Many of the colos that have been out there, and of course the internet is still relatively young, but many of the colos that have been out there have never once had an outage. Many of them have never once even had to use a UPS, and even if they have, they've still never had an outage. So colos are normally going to be very reliable ways of managing your servers. So that's just one alternative there, and we don't always have that, but you will, in this case at least, have a web in-house, for example, here. You might also have a mail relay, and that might be because we want to receive internet mail, and then we want to have this mail relay. Maybe it's got also some spam filtering on it or something like that. Then it may filter that through and then pass it through to an internal mail server right here. And then our users on our network will send their mail through this mail server, which in turn goes back through this mail relay, which is connected to the internet through this DMZ, and then sends it back out here. So that's another implementation of how you might use mail. And then we might also have a DNS server out here. Now, DNS server design is going to really be important. We'll be looking at that a little bit later on. But you'll often have your public namespace out here. So I might have nuggetlab.com out here. And that's what DNS out here hosts. But I can't have the same public namespace that I do privately. I mean, you could, but you're opening yourself up to a lot of security vulnerabilities that way, and it's very seldom, if ever, a good idea. So maybe we'd have on the internal, we might have nuggetlab.local or something like that, and lab.local. And so we might use this domain and this DNS and Active Directory domain internally. Now let's look at some things in terms of the physical network here as well. First of all, notice that we've got 3 floors within this network, and each one of these floors can be considered a horizontal network because that's horizontally along this first floor. So horizontal network here, here, and here. And then we have this over here, which is what we would consider then our vertical network, because that connects each one of the floors vertically. We can also consider this our backbone network here as well, because it's these routers that connect each one of these floors together. Now, in some respects, this network design that I've got here is, I don't think antiquated is the right word, but let's just call it a more fundamental design. There are other ways of improving this network in terms of its performance and so forth. This is also relative somewhat to how many actual workstations I have up here. I mean, after all, there's not really just 3 workstations up here. There might be 300, there might be 3,000 workstations on that floor, depending on the size of that building. And so if it's quite a few workstations up there, then I'm not going to connect them all to a hub. And that's because of the nature of Ethernet. And we're assuming Ethernet here because that's pretty much company standard for most networks these days. And because Ethernet is a collision-based network, what happens is if this host is trying to communicate and it says, hey, I have a message to send out, and this host also has a message to send out, and they both try to send out a message at the same time, then what happens is a collision occurs, and both of the packets are destroyed. And then what happens is each host will automatically calculate a back-off interval where it'll attempt to resend the packet at a random period of time within a period of time. Well, if you get too many of these collisions going on, then you get a whole bunch of retransmits going on, and then you get a very, very chatty network. And that's part of the problem that you're going to have with a hub, because a hub hears all traffic from all hosts, and then it just repeats it. We also call these repeaters. Also just repeats that same signal back out of all of its other ports. And that's where we get quite a lot of network traffic on that. And if I've got 25 clients up there, if I've got even 50 clients up there, I think I could probably live with 2 or 3 hubs up there that are handling all of that. But if I get too much more than that, and it depends on how busy these workstations are as well, then that's not going to be the ideal situation. In that case, what I will probably want to do is to switch this to a switch. No pun intended. Switch it to a switch. And what happens with the switch is, when this host sends out a message, it goes down to the switch, and then this switch will be able to identify each of the hosts plugged into it. It can do it by, depending on whether it's a layer 2 or a layer 3 switch, it can do it by MAC address. When you turn on a layer 2 switch, it just learns in a very short period of time the MAC address from each one of these workstations, because all these workstations will send out things like keep alive packets or any other ordinary network traffic. So the minute this administrator plugs in all those patch cables to this switch, it learns who everybody is. So when this workstation tries to send something that's destined for whatever the MAC address is for this host, it'll send it into this port and send it right back out, only that specific port that goes right to that specific workstation. Now the advantage of that is, if this client here were transmitting, and this was back to a hub now, if this were transmitting and it was trying to contact this client, and this client were also transmitting at the same time that this hub was sending out the message back out of all of the ports, then we would have a collision here, and we would have to retransmit. But now since it's a switch, it's going in one port and directly out of another, and I don't care if this guy's trying to communicate or not. It doesn't affect my network traffic at that particular instance. So you're going to see a lot, dramatically fewer collisions and a great increase in performance. Also, on a hub, all the bandwidth, if we're on let's say 100 megabit per second network, which is kind of becoming the commonplace network nowadays, well, all of these hosts really are splitting up that 100 megabit per second speed on that hub. With a switch, I pretty much have dedicated bandwidth between these two hosts through the switch. So they're much faster from that kind of a performance benefit as well. Now, for those of you that are acquainted with Cisco networking design and all that kind of stuff, you might look at this as well and say, boy, there's a lot of different things they could do. And we're not going to address all the optimizations that could take place. We're just addressing some of the fundamentals here. But one of the things you might also look at, again, if you're more experienced with networking or you're Cisco certified, is these routers here as well. Routers are really, we're not really using them as much as we used to. Of course, you still got to use them at places like your WAN connections, this internet connection over here, and this connection over here between the perimeter network. Those still are important places for those. But depending upon how many clients you have on the network, it's even feasible to replace this router with a switch, and this router with a switch, and this router with a switch, and then to work with the VLANs, which certain kinds of switches are capable of kind of concatenating together multiple logical subnets into a single physical subnet. And what would eventually happen then is if we replaced all of this, well, actually, at least these two, with switches, this would still have to be a router because it's on the DMZ. But if we replace these with switches and all the rest of these hubs with switches, we'd essentially have these two networks concatenated into a single network. And we'd probably use a VLAN to do that. You could also use something that's included in Microsoft's own DHCP product, and it's kind of similar to a VLAN, and that would be where you could use superscopes. We'll be looking at superscopes also when we get more into DHCP. But that might be something like, maybe we've got a subnet scheme of 10.10.10.0 with 24-bit subnet mask, and we'll be looking at IP addressing again shortly here. And then the next network, maybe this one down here, would be 10.10.11.0, 24-bit subnet mask. What you can do with VLANs or with superscopes is concatenate these into a single subnet. So even though by design they're supposed to be two separate subnets, you can make them a single subnet, and then basically make these two physical networks combined into one physical network and one logical network as well. And that's just an option. You don't have to do that. Making a SuperNet or using a VLAN doesn't mean that you're a better network administrator. It's just another option that you can use. And it doesn't work in all situations. I mean, if we've already got quite a lot of hosts up here and quite a lot of hosts down here, and it's a pretty busy network, then to replace all of these with switches might not be a good idea. We might want to break up these collision domains because this also represents a broadcast domain. You see, we really have two things going on here. Ethernet is a collision domain where we will have the potential of multiple hosts communicating at the same time. That's when we get this back-off timer thing where we have to retransmit and all that. We also have broadcast. What if this host here doesn't know the IP address, or rather the MAC address of the host that it's trying to communicate with? Well, ultimately, when it tries to find a host, it sends out a broadcast saying who has 10.10.10.6, and it'll broadcast that out. Well, whether you have a hub, it'll broadcast that out of all its ports. If you have a switch, since it's a broadcast, it doesn't know which host it's supposed to send it out to, so it can't be specific like this. It will also broadcast out to all of the hosts again on the switch the same way that a hub would have. So if you have some kind of a network application or some kind of network functionality that has quite a lot of broadcasting involved in it, then you don't get that much of a benefit out of a switch just for the purposes of broadcasting. In that case, you might want to keep a router here instead of making this a switch, because a switch will broadcast out of all of its ports, not only on this network, but also on this network, all of the broadcast packets. Whereas a router will block the broadcast packets here, and it will keep them only on this local network. Well, then you might be thinking, well, what if this host up here was trying to communicate with a host that was on this network down here? Well, then it would still have to send that packet out, but then because of the route table, it would direct it to its default gateway, which would be this router. And then it would be the responsibility of this router to send it to this router, which in turn would then be responsible for sending it on to this network. And then it would look for whoever has 10.10.11.6 or whatever else the network ID might be down here. Now, a lot of what I've been talking about here with switches and routers operate at a couple of the different levels of the OSI model, which I've listed over here on the left-hand side. And you don't necessarily have to know all of these layers for Microsoft purposes right now, but the bottom three are of particular interest to us right now. First of all, there's the physical layer, where we actually put something on the network card or on the NIC to put it on the wire. It actually goes onto the wire itself at that point and is transported there. And then the second layer here would be the data link layer, where, and I don't know if you can see this because of the computer in the background, but that's MAC, or MAC address. And that's how hosts will communicate with one another using the MAC address. You see, ultimately, one host does not communicate to another based upon its IP address. It has to resolve the IP address to a MAC address. Once it finds the MAC address, then it actually can send it to the physical network card, because the physical network card has that MAC address. And then there's the network IP address as well. Now, this is where our routers are going to take place. And routers will identify how to send a packet to a destination based upon the IP address. So if I'm on the 10.10.10. network up here, 10.10. Network up here, and this network down here is separated by a router at the 10.10.11. network, then what we can have here is the ability to use a router to operate at the network layer, and it can see that I'm trying to send an IP address, or send to an IP address at 10.10.11.4 from this host right here. Well, then it will know that that's not on its own network because of its route table on this local workstation, which means that it'll send it to its default gateway, which would be this router here. This router will then be responsible to send it on to, because of its route table, this router here, because it knows that it is going to be able to handle the 10.10.11.0 network ID. And since we're operating only on IP addresses here, we're operating at the network layer of the OSI model when we're using these routers. Now, we can also operate at the data link layer, which would be what we use when we use conventional kinds of switches, or layer 2 switches. And switches identify these hosts based upon their MAC address instead. You see, we have a tendency to think that hosts communicate via IP address. Well, that's just kind of what gets them started. Ultimately, they're looking for a MAC address. So if this computer here is 10.10.10.6, and it's trying to communicate with 10.10.10.8 over here on the other side, what it's going to wind up doing is it's going to do an ARP request, an address resolution protocol packet that's going to go out. It's a broadcast, and it says, tell me who's got 10.10.10.8. And let's go ahead and do a network monitor packet capture, and we'll go ahead and see that in action. So I'll ping that host 10.10.10.21. And when I stop the packet capture to look for the traffic, I'm going to scroll on down here, and we're going to see that there's an ARP request for 10.10.10. Well, there's .5. That's not the one I want. There it is. 10.10.10.21. And all it's doing is it's a broadcast packet, and you can see it right there. It's a broadcast going from this local host to a broadcast. And it's saying, tell me who in the world's got this IP address. And then the reply is going to come back from the correct MAC address. You see, when it sends out this request, it includes the sender's hardware address in it. That way, when whoever has that address says, oh, hey, that's me, then it'll send back and it'll know which MAC address to send the reply back to, and it'll send it from its MAC address, which we see right here, to this local host. And it knows how to do that because, again, the MAC address was included in the initial broadcast. And from that point, both parties know each other's MAC address, and they're able to then communicate on the wire one with the other. Now, in terms of switches and how that works, the switch also learns all the MAC addresses on the network. And like I mentioned earlier, since this switch knows which host is connected to this port that has the specific MAC address and operating at the layer 2 data link layer, then it will be able to send any other packets besides the initial broadcast for this host back out to that specific port. Now, if we had decided to work on layer 3 switches and use those instead, they would work on the IP addressing, and you can configure the switches that are layer 3 switches so that they can identify IP addresses out of each of these ports as well. And in that case, it would send the packet to .8 based upon its IP address, just depending on which kind of network equipment you want to get. Now I got tired of looking at all my chicken scratch, and I'm sure you did too, so I cleaned things back up to where they were here, and now I'm going to go over one other network design to consider here. Notice that I got all my servers on the same horizontal network down here on the first floor. And why would I do that? Why wouldn't I kind of spread them out to distribute the load maybe among a lot of different floors here? Well, that's because, for example, mails that are heavily utilized or servers that are heavily utilized, like my mail server right here, it's getting a lot of traffic in from this mail relay from the internet all through here onto this mail server. And because of that, I'm able to isolate all that network traffic to only this horizontal network. Anytime this host up here wants to check their mail, yeah, of course, then we go through the backbone to the first floor, and we get a little bit of traffic back and forth that way. But that's only traffic that is absolutely necessary because this client is actually pulling for their mail. If, on the other hand, I had taken this mail server and I had put it up here, and this was our corporate mail server where it was servicing all of our clients throughout the whole network, well, it's getting all kinds of traffic now, and it's going to flood this horizontal network. Why? Because we're getting a mail relay coming up through the backbone and flooding this network. We're also getting all of these clients down here that are trying to send and receive email. Well, they're going up here to this network as well. Then we have our ordinary network traffic from these workstations that go everywhere else as well. So we've really got a substantially higher level of network traffic because we put that email server up here. It would have been better off just to leave it down here. That way only necessary traffic to that email server is used on this network. Now, the exception to that might be if, let's say, that this division up here were highly secure, we had a government contract that prohibited any kind of internet-exposed email. Well, that would make this just a departmental email server then. And in that case, that might make some sense because it's only going to service requests to and from these particular workstations. None of the other workstations here have any business with it. And none of these servers have any business with this email server. So we can actually isolate traffic here by keeping it on this network only. And that would also, in this kind of a scenario, be more secure. So there are situations in which you want to make it departmental and on a specific floor like I've got there. But most of the time, you want to isolate them as much as possible and group them together like I had down here. Here I've cleaned up again back to our original diagram, and I want to take a look at some things we can do to make this more efficient. First of all, again, we have hubs and all these locations. We talked about the benefits of switches there. We also have routers over here on this vertical network. Now, the reason why I used this vertical network layout is because that's kind of a common Microsoft layout that you'll see in a lot of Microsoft documentation. In my opinion, this is not that efficient. I'm not sure why Microsoft really does this. I mean, in my view, we have a couple of routers here where we've spent thousands of dollars that we didn't even need to use. Routers, at the bare minimum, if you get the bargain basement one off of eBay, it can handle 2 connections, in other words, 2 segments. But anything that's used in a corporation is going to be able to handle multiple segments at a time, maybe even dozens of segments at a time. So I really only need one router here. I can get rid of this router and get rid of this router and then hook my DMZ up to this router. And we're taking a look at that in another diagram where I've actually done that. we look at it over here, we see that that's exactly what's happened. So I've saved myself some money on these routers, or I can ship them off to some other office somewhere. And then again, I put my switches over here as well. Now, the other thing to consider here as well is what kind of protocols I'm going to be using. In almost anything I do, we're only going to be assuming TCP/IP. I mean, why use anything else? We're going to need to communicate on the internet, so we need TCP/IP there. It's pretty efficient in terms of the addressing, especially if you use private network addressing, and so forth. Plus, in our case, what else would we use? The other two protocols you can use in a common Microsoft implementation would be IPX/SPX, which gives you compatibility with Novell NetWare, which we don't have any in this environment. And even if we did, Novell is capable of using TCP/IP in current versions anyway. So the only reason why I would need to use it is if I had an older Novell solution down here. By the way, Windows 2000 and the Novell servers that came out at the time of Windows 2000 was also available. Both use RFC-compliant TCP/IP stacks, but guess what? For some strange reason, they were incompatible with one another. So in some of those earlier implementations, you'd have to use both TCP/IP and IPX/SPX in Windows 2000. But if you're using all current clients now, you shouldn't have to do that. Plus, the other thing you could use, and boy, heaven forbid that we have to use this, would be, in addition to IPX, let me just write that down so if you're not familiar with it, IPX/SPX, which is again what we're going to use for Novell NetWare. You could also use NetBEUI. NetBEUI, E-U-I, it's got a strange spelling, so I always got to think about it when I spell it. NetBEUI is strictly really a single network protocol. Does not work well in routed environments, and it's very chatty. NetBEUI is an old networking protocol from Microsoft's previous editions of their products, and you don't even get it by default with Windows Server 2003. You have to jump through some hoops to be able to get it installed on a Windows Server 2003 server. It's not in add remove programs or any of that kind of stuff. You actually have to copy certain files from the CD-ROM to the local server in order to install NetBEUI. Now, Microsoft recommends that if you have network connectivity problems, to go ahead and install NetBEUI, and then if you can communicate using NetBEUI, then you know that the problem is not with your network card, it's somewhere in your TCP/IP stack. I think that's one of the most ridiculous suggestions I've ever heard. No offense to Microsoft, especially since I really do believe that they do most of what they do in an excellent way, and they're very, very professional. However, that's not one of the best suggestions I've ever seen. I mean, if I'm having trouble with TCP/IP, we're going to be looking later on at some of the tools you can use to resolve some of those problems. But if I'm having trouble with TCP/IP, I'm going to just ping other hosts, see if I can reach them. If I can't ping them, then I'll ping my loopback address. If I can't ping my loopback address, that tells me that I do have a problem with a TCP/IP stack. I don't have to install NetBEUI in order to determine whether I've got a problem with my TCP/IP stack. And sometimes they'll also say to install IPX/SPX to again, by elimination, seeing if you have trouble with your TCP/IP stack. And again, I don't see much sense in that either, because the TCP/IP troubleshooting tools should be sufficient to troubleshoot TCP/IP. Now, another component that I don't really have on the picture here is the physical security of this particular location. I mean, especially for this floor right here, we want to physically secure this server room. And we've talked about that a little bit in the past. You'll have a door that opens here, and we'll have key card access, magnetic card access, you know, DNA samples, I don't know, something like that, to make sure that only the appropriate people can get in through this door. Also, we're not going to have a window here to the outside world that people can just peek in and look at our server or smash the window and grab our stuff to the outside exterior part of the building, like we did in that one building that I talked about. Now, there are locations where you'll have windows there, and some places I've gone to, there's a kind of show-off windows. I mean, I went to, used to teach the IT departments up at Hewlett-Packard, and they'll have windows there just because they have such sexy servers that they just show them off to the world. But that's because even where you can see those from, that's also a secured area. And I've also seen servers visible from corridors and things like that at Intel and at Microsoft and other places that I've been. But again, there the difference is those are not windows to the outside world where someone can throw a rock through the window and grab all of your stuff. Instead, those are going to be more internal windows where the area is already secure anyway. And then another thing to think about is actually the cable connections themselves. I mean, this is not physically how these are usually connected. It's not the complete picture there. Here I'll have a workstation, and my network cable, my patch cable, is probably going to come out of there and go into maybe the bottom of a cubicle somewhere down here. There's my cubicle wall, for example. And then out of the cubicle wall up at the top, it'll go up into the ceiling tiles up here. And then somewhere off the end of this, it'll come down into a wall where I've got a patch panel down here. And then this is where all my cables are actually coming through into the back of this patch panel. And then in the patch panel, I'll have yet another drop cable that will go to my switch. That's not always how it goes, but that might be a very common scenario in how this works. Now, the thing to keep in mind is I don't want this patch panel to be available to the public either, or even to passersby, where visitors might be able to get in there and just do vandalizing or something like that. Or when it's bring your kid to work day, where some 5-year-old goes in there and says, "Oh, hey, look at all these fancy little plugs," starts unplugging different stuff. So make sure that even those patch panels are relatively secure. And some of them just have metal doors on them that you can lock, kind of like an electrical lockbox kind of a thing as well. In this nugget, we took a look at network design, and we saw that although Microsoft in some cases is starting to say goodbye to the DMZ, that's still the official Microsoft answer, so we still have a DMZ, or a perimeter network, as it's also called. We saw in a multi-story building where you might have horizontal networks on various floors of your network, and then you'll have a vertical network which comprises the backbone of that network. Now, the vertical network is also a routed environment in most cases, and we saw that we can trim that down apart from the default Microsoft diagram into a more efficient network design using a single router in some cases. Now, we also took a look at hubs. That's how we're going to connect multiple hosts on a single segment. But hubs can really be chatty, and they're not very efficient in terms of network traffic. They're just repeaters. So we can, in some cases, substitute switches instead, which are much faster and more efficient. And then in our next nugget, we'll take a look at, again, that same physical diagram, and we'll see that we need to segment that into multiple logical networks using TCP/IP addressing in both a public and a private addressing scheme. Well, that's it for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.